For this worksheet, we're going to be working through some challenge problems. And these problems necessitate you to connect ideas, to work through different types of problems where you're going to have to problem solve and really think through what the problem is asking. So let's jump in with the first one. The recommended dietary allowance for ascorbic acid, which is vitamin C, for males 19 years and older is 90 milligrams per day. An average orange provides about 55% of this requirement. It takes approximately 4 oranges to obtain 1 cup of juice. What is the molar concentration of ascorbic acid in 1 cup of orange juice? So, molarity is what they're asking for when they say molar concentration. Formula for molarity is moles of solute per liter of solution. So the solute is the vitamin C. So we need to get from 90 milligrams per day, which is the recommended dietary allowance, and then the amount of oranges, basically the amount of juice in the 4 oranges. We have to get this information coordinated to get 2 moles of solute. And we have to get from cups of orange juice to liters of orange juice. So you can set this up however you want. I'm going to use train tracks or dimensional analysis for it all, but if you want to set this up in different parts, that's perfectly fine as long as you are very clear in the work that you are showing. If I can't track your work and see what you're doing, I can't give you partial credit. So be very clear and very neat in what you do. Okay, so let's start with this 90 milligrams per day. Now, when in doubt, get to moles. So first thing we're going to need to do is convert milligram to gram, because I don't know a relationship between mole and milligram, but I do know a relationship between mole and gram. So 1 is goes next to gram because gram is bigger. 1,000 milligrams is in 1 gram, and my unit milligram cancels. Next, I can get to mole. So gram can come down, mole goes to the top. So the molar mass is 176.14 grams in 1 mole. So this would be the amount of moles of ascorbic acid or vitamin C required each day. So now let's figure out 1 cup of orange juice, what the molar concentration is. So 1 mole, or 90 milligrams, 55% of that is provided by 1 orange. So I'm basically multiplying the mole times 50%, or the 90 milligrams times 50%. Then 4 oranges give me 1 cup. So oranges cancel. So I'm left with mole on the top, which is what I want. Now I want to convert cup to liter. So I looked on the conversion sheet I gave you. I will give you whatever conversions you need for this. You're not expected to know relationships between the English and the metric system. So I did 4 cups is 1 quart. 1 quart is 1 gallon. And then 1 gallon is 3.785 liters. So quarts cancels, cups cancels, gallons cancels. I am left with moles per liter. And then when I do the answer and I get the answer, I get 4.75 times 10 to the minus 3 moles per liter, which is also molarity. Question number 2. We have a sample of SF6 at STP, and that particular sample has 112.41 grams of fluorine. We want to know what the volume of the sample is. Now, because it's mentioning volume and STP, somewhere we're going to have to use 22.4 liters equals 1 mole. Now, this sample, it's telling us the amount of fluorine that's in the sample, not the amount of SF6. So what we're going to have to do is we're going to have to look at the relationship of part to whole. So remember, I have 1 sulfur for every 6 fluorines for every 1 SF6. That subscript tells us relationship of the part to the whole when we're in a unit of molecule or if we're in a unit of mole. So if I have 112.4 grams of fluorine, first thing I'm going to want to do is get to moles. Because once you're at mole, that's our jumping off point to get to just about any other unit. So grams comes down, mole goes to the top, and I have 19 grams of fluorine for every 1 mole. Now that I know how many moles of fluorine I have, I can figure out how many moles of SF6 I have, because for every 6 moles of fluorine I have 1 mole of SF6. That cancels. And now I can get to volume of SF6 because I know that 1 mole of any gas at STP occupies 22.4 liters. And so moles of SF6 cancel, grams of fluorine cancel, and then I multiply this out and I get 22.1 liters of SF6. So question 3, we have a 10% by mass solution of sodium hydroxide, and it has a molar concentration of 2.778 molar. What is the density of the solution in grams per milliliter? Now, we can set this up with a chart, or we can just logically think it through. So why don't we set in the answer key, I have it set up without the chart, but we'll set it up with the chart now just to reinforce using the chart. So we're going to have solute, we're going to have solvent, and we're going to have solution. We're going to have moles across the top, we're going to have mass, and we're going to have volume. Now we need to be very clear what we are looking for when we are looking for density of the solution. Density of the solution is mass of the solution divided by volume of the solution. So I need this value and I need this value. I need both of those. So let's look and see what information we can use and what we can get. So I'm given 2 different concentrations. I am going to need to assume one piece of information about one of the concentrations and use the other as a conversion factor. So I am using molarity as my jumping off point to say that I have 2.778 moles per liter of solution. So liter of solution is 1,000 milliliters. So by using my molarity, what that allows me to do is automatically get the volume part of my density. Now what I need to do is I need to figure out the mass of my solution. So from moles of solute, I can get to mass because I can use molar mass of sodium hydroxide. So if I have 2.778 moles of sodium hydroxide, 1 mole has a molar mass of 58.44 grams. So which means I have 111.12 grams of sodium hydroxide. Now from here, I need to get to mass of the solution. And this is where I'm going to use the other information that's given as a conversion factor. So if I know my mass percent, remember my mass percent is going to be mass of solute per total mass of solution. So I do know my mass percent, that's 10%. I do know my mass of the solute, it's 111.12 grams. Now I can get my total mass. Now be careful with your algebra. In order to solve for this, I need to take the mass, 111.12, divided by the 10%, or divided by 0.1. So my total mass is going to be 1,111.2 grams. And so that goes here. Now I have the information I need to get the density of the solution. The density of the solution is the mass of the solution, which I just calculated, divided by the volume of the solution in milliliters, which is what I assumed at the beginning of the problem. So the density is going to be 111.2 grams divided by 1,000 milliliters, and the density is 1.111 gram per milliliter. Fourth problem, a sample of an unknown gas has a mass of 0.8421 grams and occupies 1.175 liters at STP. We want to know if it's NH3, CH4, or H2O. Really, the only way that we can figure out what it is to figure out what the molar mass of this unknown is. Now, to get to a molar mass, and this is where understanding units is really going to help you. The unit for molar mass is grams per mole. So if I know how many grams I have, and I know how many moles that's equal to, I take grams, I divide by moles, I can get a molar mass. Well, the problem tells us I have that many grams. So I have 0.8421 grams. Now I need to solve for moles. Well, do I have information in the problem to get to moles? I sure do, because I know that a certain volume of that gas at STP. And then I can use 22.4 to figure out moles. So I have 1.175 liters. 1 mole has a volume of 22.4 liters. I take the 1.175 divided by 22.4, and I get 0.05246 moles. Then I take my mass that's given in the problem, divide by moles, the amount of moles that it's equal to, and I get a molar mass equal to 16.0 grams per mole. Then I have to calculate the molar masses of the NH3, the CH4, the H2O, whichever one matches 16, that's what the unknown is. So the molar mass of NH3 is 17.04. The molar mass of CH4 is 16.04. And the molar mass of H2O is 18.02. So the unknown is CH4. Question 5. We have 1.5 liters of 0.225 molar aluminum chloride solution. So we make it, and then we realize we need to add more of the solute to make it more concentrated, because we want a 0.65 molar solution. How much more do we need to add in grams? Now we're going to assume the aluminum chloride does not affect the total volume. So we have to assume that we start with 1.5 liters and we end with 1.5 liters. So molarity is equal to moles of solute per liter of solution. So the solution that I first make, I have 0.225 molar is moles divided by 1.50 liters, which means the amount of moles that I added initially was 0.3375. And this is the amount that I have in the solution I just made. The amount of moles in the solution I want, I repeat the calculation. I want a 0.650 molar solution. I solve for moles. and I'm still going to have 1.5 liters. So the moles that I want to have are going to be 0.975. And this is what I need. The difference between the two is what I need to add. In the answer key, what I did was I converted each of these to grams and then took the difference. So if we have 0.3375, I put mole on the bottom. Molar mass is 133.33 grams. And I get 45 grams. And then 0.975. Convert that to grams. And I get 130 grams. The difference between the two is 85 grams. So this is what I need to add. The sixth question. Quinine, which is a natural ingredient found in the bark of the cinchona tree, can be used as a treatment for malaria. If you've ever tasted tonic water has quinine in it. That's what gives it that unique flavor. Contains the elements carbon, hydrogen, nitrogen, and oxygen. Now this, if you read the rest of the problem, it's burned in excess oxygen. It produces a certain amount of CO2 and water, certain amount of nitrogen. We want to get the empirical molecular formula. So this is a combustion analysis problem plus a little bit extra work. So first, let's figure out how much carbon we have. So it produces, after we burn that amount of quinine, we get this much CO2. Now remember, the carbon that was in the quinine is converted to CO2. So we assume that all the carbon in the quinine went to the CO2. So we need to figure out how much carbon is in that much carbon dioxide. So I have 1.321 grams of CO2. I know that based on molar mass and based on the percent composition, that for every one CO2, 12.01 grams, which is the molar mass of the carbon, per total mass, 44.01 grams, that's going to give us the mass percent of the carbon. So I multiply this out, and I get 0.3597 grams. To get the mass of hydrogen, again, I have to assume that all of the hydrogen that's in the quinine is converted to the hydrogen that's in the water. So I do a percent composition to figure out the mass of hydrogen that's in that much water. So 0.325 grams of water. And I set up the ratio that it's 2 times 1.01 per 18.02 grams. And this will tell us the amount of hydrogen, excuse me, that's in that sample of water. So I get 0.03643 grams of hydrogen. It tells us in the problem, we get this much nitrogen. So my nitrogen, I'm going to put it over on this side, and you'll see why in a minute. So we have that much nitrogen. So this is I forgot to label it, carbon, hydrogen, nitrogen. Now read the problem carefully because there's also oxygen in there. And there's no information about the oxygen in the problem. So we have to figure it out by difference. So the amount of oxygen, I started with 0.487 grams total. And 0.3597 of that is carbon. 0.03643 grams of that is hydrogen. And 0.0421 grams of that is nitrogen. So the remaining amount, which is equal to 0.04877 grams, is oxygen. Now I'm ready to jump in and do the empirical formula. And so we are on the second part of that poem, percent to mass. Okay, we're at mass. Now we do mass to moles. So 1 mole of carbon is 12.01 grams. 1 mole of hydrogen is 1.01 grams. 1 mole of nitrogen is 14.01 grams. And 1 mole of oxygen is 16 grams. And I get those values from the periodic table. And we get the following mole values: 0.02995. We get 0.03607, 0.00300, and 0.00305. So we've done the percent to mass, mass to moles. Now we divide by smallest. And the smallest is 0.003. So I divide everything by that so that I can convert this to a mole ratio. And the values I get are 10, 12, 1, and 1. So what that means is the empirical formula is C10, H12, NO. Now, to get my molecular formula, remember, I need to compare my empirical to my molecular. So the factor, how many empiricals there are, is equal to the molar mass of the molecular divided by the molar mass of the empirical. The molar mass of the molecular is given in the problem, 324. The molar mass of the empirical, you calculate using your molar masses, and I get 162. So I take that 162 and I put it underneath the molar mass of the molecular, and I get a factor of 2. So that means there are 2 empiricals in my molecular. So I multiply every subscript by 2. So my answer is C20, H24, N2, O2. Question 7. We can make pure oxygen by heating a compound that contains potassium, chlorine, and oxygen. So I take this compound, I take 3.22 grams of it, I decompose it, oxygen's given off, and I get this much KCl. And I want to figure out what the empirical formula is. So to get the empirical formula, I need to know how much potassium there is, how much chlorine there is, how much oxygen there is. Oxygen is going to be the easiest one, so I'm going to sort of figure that out first. Law of conservation of mass, if I start with 3.22 grams, and 1.96 of that is KCl, the remainder has to be oxygen. So I get 1.26 grams of oxygen. Okay. For the KCl, I'm going to do the same thing as if this was a combustion analysis. I'm going to multiply the mass of the sample times the percent potassium times the percent chlorine that was in that sample. So if I have 1.96 grams, I multiply that times the mass percent of potassium in potassium chloride. So potassium has a molar mass of 39.10. The total molar mass is 74.55. And I get 1.028 grams. I repeat the process, but this time I use the molar mass of chlorine. So I do the percent composition of chlorine in KCl. So 35.45 divided by 74.55, and I get 0.932. Now I'm ready to jump in and do the empirical formula. So percent to mass, we already have the mass. Mass to moles, so I'm going to divide by molar mass. So 1 mole, 39.10, 0.02629. Divide by molar mass of chlorine. And I get 0.02629. And now I divide by the mass of oxygen, which is 16. and I get 0.07875 moles. So this tells me how many moles of each element there is, but I need to get the mole ratio. So I divide by the smallest, 0.02629, and I get 1, 1. This is like 2.99, which I can round to 3. And so my ratio is 1 to 1 to 3. My empirical formula is KCl03. Question 8, we're dealing with hemoglobin. And so hemoglobin is the compound found in human blood that is responsible for carrying oxygen. And it contains 0.3335% of iron by mass. So we know it's mass percent. We know that 1 molecule of hemoglobin contains 4 atoms of iron. We want to know what the molecular mass is of hemoglobin. What's the molar mass? Remember, molar mass, it has the unit of grams per mole. So if I know how many grams I have, and I know how many moles I have, I can very easily get the molar mass. Now, when given a mass percent, what we're going to start with is assuming 100 grams total. Because if we assume 100 grams total, we know now that we have 0.3335 grams of iron. Then what I can do is I can convert grams of iron, moles of iron, very easily because I know the molar mass of iron. So remember, when in doubt, go to moles. So grams comes down, mole goes to the top. 1 mole has a mass of 55.85. I get that from the periodic table. Now, how do we get from iron to hemoglobin? Well, it tells us that 1 molecule contains 4 atoms of iron. There's our jumping point. There's our point where we can go from the part to the whole. We can go from the amount of iron to the amount of hemoglobin. So 4 moles of iron is per every 1 mole of hemoglobin. So now my moles of iron cancel, and I get 1.493 times 10 to the minus 3 moles of hemoglobin. Well, I know the mass that I have of hemoglobin because I assumed 100 grams total. I know the moles I have of hemoglobin. I just calculated it. So now if I take 100 grams, I divide by 1.493 times 10 to the minus 3 moles, I get a molar mass of 66,979. With sig figs, it's 6.698 times 10 to the 4 grams per mole. Do not get nervous that you get this really huge number. Molar masses of proteins can be very, very, very high. We can have 10,000, we can have up to 100,000 because they're huge molecules. So this number is on the right scale for a molar mass of a biological molecule. All right, we're almost at the end. Question 9. So we have this compound, C17H21NO4, and we mix it with sugar, which has the formula C12H22O11. We take this mixture, we burn it, and we get 2 milligrams of carbon dioxide. And we want to know what the percent sugar is in the mixture. There's not a lot of information there. And what we want is ultimately what is the composition of the mixture that we have up here. Well, I'm going to tell you right now, this is going to be a system of equations, and we're going to have to set up relationships that we know. Okay? I'm going to say that C17H21 is going to be X, and I'm going to say the sugar is going to be Y. So the amount that I start with before I carry out the combustion reaction, I'm going to say X plus Y has a total mass of 1. And I'm going to use the unit gram. I'm not going to convert to milligram. And the reason is if I convert to milligram now and then convert to gram at the end, the conversion factor cancels out. And so it's just easier for me to work with a number 1 rather than 0.001. So I'm just going to sort of put everything into grams. So this is one relationship. The other relationship is the grams of carbon in X, which is the C17H21NO4, plus the grams of carbon in the sugar has to equal the grams of carbon in the CO2. And that number is equal to 2 grams of carbon dioxide. And I need to figure out how much carbon is in the 2 grams of carbon dioxide. And all of that carbon came from C17 and C12. Well, I can write a generic formula, to write Y there, for grams of carbon in X, grams of carbon in Y, and I can figure out the grams of carbon in CO2. So the grams of carbon in X is going to be the following. So the amount of X that I had is equal to, or multiply that times the percent composition of carbon in this compound. So it's going to be 17 times 12.01 divided by the molar mass of the whole substance, which is 303.35. So if I were to set up the percent composition of carbon in this compound, I would set it up this way. I multiply that times the amount of X I started with. That's the mass of carbon that I had to start with. Then I add that, the initial mass of Y, times the percent carbon in the sugar. So 12 times 12.01 divided by the molar mass of the sugar, which is 342.30. That is going to be equal to the mass of carbon in the 2 grams of carbon dioxide. So if I have 2 grams, it's going to be times 12.01 divided by 44.01. And now I can simplify this and I get the following. I get 0.6731 times X plus 0.4210 times Y is equal to 0.5458. And the 0.5458 is the grams of carbon that is associated with 2 grams of carbon dioxide. So now I have 2 formulas and 2 variables. So I'm going to solve for X in this equation. X is equal to 1 minus Y. Oops, I wrote the wrong thing. 1 minus Y. I am then going to take 1 minus Y and plug that in here for X. So then I get 0.6731, 1 minus Y, plus 0.4210Y equals 0.5458 grams. Solve this. I'm going to wave my magic algebra wand, and I get Y equals 0.5046 grams. Now, Y, I said, was the sugar. So that's the mass of sugar that was present in the original mixture. And it's asking us, what is the percent sugar? Well, I know the mass of the sugar. It's 0.5046. I know the mass of the total sample, what I started with. It was 1 gram. Multiply that times 100. The sample had 50.5. It's with the significant figures. We're going to need, it's going to be 4.56% sugar to start with. Last question. This is a variation on ones that we've done on other worksheets. We have 1.443 grams of a metal. We reacts with oxygen, and it forms 1.683 grams of an oxide. An oxide is just a compound that has oxygen in it, and the oxide has the formula M2O3. We want to figure out what element M is. On the answer key, I have it done two different ways. I'm actually going to do it only one of the ways. You can look at the answer key for the other. And I'm going to do it the way of using mostly train tracks and using the relationships of the subscripts to the whole, the part to the whole. So I can figure out easily how much oxygen I have by the law of conservation of mass, because I start with this much of the metal and I end up with this much of the compound. The difference has to be the oxygen that reacted. So my grams of oxygen is 1.683 minus 1.443, and I get 0.24 grams of oxygen. From the grams of oxygen, I can get the moles of M2O3. Now remember, molar mass is grams per mole. So if I know the grams of M2O3, which I do, and I know the moles of M2O3, which I can figure out, I can get the molar mass of M2O3. So if I have 0.24 grams of oxygen, and this would have a 0 after it, 1 mole has 16 grams. And I know from the formula that I have 3 moles of oxygen per every 1 mole of M2O3. So I have 0.005 moles of M2O3. Now I have the mole value. I take my grams, 1.683, divided by 0.005, and I get a molar mass of 336.6 grams per mole. That's the molar mass of M2O3. I now want to calculate the molar mass of just M. So it's going to be 336.6 equals 2 times the mass of M plus 3 times the mass of oxygen. So when I solve for this, I get a molar mass of 144.3 grams per mole. I look on my periodic table, that is neodymium.